Assalamu alaikum wa rahmatullahi wa barakatuh. In this video, we'll talk about the relation between temperature and rate constant, T and K. Okay, before we talk about temperature and rate constant, we'll talk about the temperature and the collisions. So we will have this diagram. Let's do this diagram here. We have here energy for x-axis, and for y-axis, we have number of collisions. Okay, and we have an area here for the curve, and this area or this point, sorry, we have a point here. This point is representing the activation energy. Okay, so I will draw a line for the activation energy. What this line means that this is at this point, if we have a collision with this energy, so it can form the activated complex and can form a product. And also after this area, all the collisions will be happening after this area, you will have the activated complex and enough energy to form the product. But before, so the energy of the collisions will be lower, so they can form product. Let's start by taking two temperature. I will take T1. Let's say that T1 is 20. Okay, so here T1 is low energy. So what will happen here as the low energy? So we have molecules and they will collide with each other. But as we have low energy, it means that number of the collisions or the collisions will be with less energy, but small numbers will reach the activation energy. So starting from this point and the area under the curve here, this will be representing number of collisions or effective collisions. With this effective collisions will form the activated complex and will form the product because they have enough energy, which is called the activation energy. But the area representing here in this area will represent the number of collisions which they can't form the activated complex, or they can't form the activated complex because they don't have enough energy, which is activated. They didn't reach this point, which is the activation energy. Okay, let's take another temperature. Okay, sorry. Let's take another temperature, T2, and we will take it as 100. If we take T2 as 100, so what we have here, we have more temperature, it means we have more energy. So it means more collisions can form the activated complex. And if we draw the diagram here, so we will have this point, and this point is higher than the one with green because here we have more energy. So it means that we have more number. Remember that this one represents the number of collisions with higher energy. So and the area under the curve here represents the number of particles with higher energy. So when they are higher than the one before, because here we have more temperature, we have higher temperature, we have more energy, so they can easily form the activated complex. And the area before the graph here, or before the activation energy, the area on the left represents the number of the collisions that they can't or they don't have enough energy, and this one is lower because, of course, with higher temperature, we will have more effective collisions. Okay, so increasing the temperature will increase the effective collisions, and it's increasing the effective collisions, it means increase the rate. So we have more effective collisions, it means the reaction will happen faster, so the rate of the reaction will be higher. Okay, let's go for Arrhenius equation. So what is Arrhenius equation? Arrhenius equation is equation to find the relation between temperature and the rate constant. Okay, and Arrhenius equation is K constant is equal to A multiplied by E to the power of EA over RT. Okay, so K is the rate constant. And actually this one should be written, let's see, like this. Okay, and A here is representing the frequency factor, and this frequency factor is representing number of collisions. Okay, so this is how the molecules will collide with each other, our number, okay, representing just like a probability of the collisions between the molecules. And EA is the activation energy. And remember that again, the activation energy is the minimum of the energy that's required to form the activated complex and then form the product. R is the universal gas constant, and this one will be used as 8.314, and the unit for this one will be joules per Kelvin mole. And T is the temperature, and temperature here also will be used or measured by Kelvin. Okay, so as we see here, the rate constant will be have a relation between the temperature. And of course, you can start to put a different temperature value and of course, and put a value for the E or the activation energy, and the R is constant, and you could calculate the value or the relation between the rate constant with the number of collisions of. And you will find that we have a direct relationship between K and temperature. It means that if you increase the temperature, so the rate constant will increase. And actually, he explains or takes the ln for the equation, and the equation will be written like ln K equals minus EA over R times 1 over T plus ln A. And here, if you draw ln K with 1 over T, here it will be 1 over T, and this will be ln K. We will find a direct relationship, a linear relationship, and this linear relationship we will have a slope, and this slope will be equal to minus EA over R. And of course, R is a constant, so this one is known. So if you have the slope, you can calculate the activation energy. And the intercept here will represent the ln A. And remember, ln A is the frequency factor. It means number of collisions or the probability of the collisions between the molecules. And this will be representing the relation between K and T. Let's have a question here. Okay, so we have a reaction, and this reaction is a first order with respect to CH3 CBr and a zero order to OH. Okay, in several experiments, the rate constant K was determined at different temperature, and if you plot ln K, so I will do what he said. So we will plot ln K. This is ln K versus 1 over T, and this is 1 over T. Okay, we will have a straight line. Okay, this is a straight line. And the straight line with the slope minus 1.10 times 10 to the negative 4 Kelvin. And the intercept, this point is 33.5. Okay, let's again try to remember what is the slope and the intercept mean. Okay, so the slope here is equal to minus EA over R, and the intercept represented ln A. Okay, so if we have the slope, which is minus EA over R, so this will be equal to minus 1.10 times 10 to the power of 4 Kelvin, and the intercept it will be 33 ln A equals to 33.5. So this is the information that we have here. Let's see what he asked for. First, determine the activation energy, okay, for this reaction. So we need to determine the value of EA. So actually we will use this formula again. So minus EA equals to minus 1.110 times 10 to the power of 4 Kelvin multiplied by the gas constant, which is 8.314. The unit for this one, it will be joules per Kelvin mole. So Kelvin will be deleted with Kelvin, and the minus will be deleted with the negative one here. So the activation energy will be equals to 9.1 times 10 to the power of 4, and the unit it will be joules per mole. Okay, so this is for A. B, determine the value for the frequency factor. So the frequency factor, which is A. So we have ln A from the intercept equal to 33.5. So we need only to take the shift for the ln or inverse ln. So this will give you A equals to 3.54 times 10 to the power of 14, and we have no unit for this one. Okay, C, calculate the value for the rate constant. So we have the rate constant K equals to A multiplied by E to the power of EA over RT. So we only substitute in the formula. So A is 3.454 times 10 to the power of 14 multiplied by E to minus EA, which is activation 0.1 times 10 to the negative to the power of 4. Or you can put the intercept, the slope over RT, and R is 8.314, and the temperature it's here is Celsius. It should be in Kelvin, so we will add 273 for this one, so it will be 289 or 298. And you can calculate this one, and the final answer will be 0.0329. And remember, the rate constant has always a unit, and we need to go again for the question here. He said, assume that the K unit is minus 1 or second minus 1. And if he didn't mention that, we need to go over here, and he said that it's a first order. So it means it will be, and here it's a 0, it means the overall order will be the first, and we know that K for the first it's S minus 1. The unit for K for the first order is S minus 1.